Differentials. We now talk about differentials. The definition is on the screen. In the definition, we symbolically treat dy as a function of two independent variables, x and dx. By that we mean, for every pair of values of x and dx, there is a unique value of dy. To illustrate the definition, we work on question 2. The differential dy is the derivative of f of x times dx. Plug the particular values of x and dx into the differential, we get the value of the differential. We'll observe some important properties before looking at the geometric interpretation of differentials. To motivate an important property of differentials, we work on question 3. In question 3, the differential dx is the derivative of g of t times dt. Plug the particular values of t and dt into the differential, we get the value of the differential. In question 3b, the differential dy is the derivative of f of x times dx. Plug the particular values of x and dx into the differential, we get the value of the differential. In question 3c, the differential dy is the derivative of the composite of the two functions times dt. Plug the particular values of t and dt into the differential, we get the value of the differential. From this question, we can see that the value of the differential calculated from the composite of two functions is the same as the value of the differential calculated in two steps. The first step is to calculate x and the dx. The second step is to use the values of x and dx to calculate dy. This is true in general. It follows from the chain rule that the differential of y with respect to t is always equal to the differential of y with respect to x if x is a function of t. This means that the differential of y with respect to t and the differential of y with respect to x always have the same form. Now, with the concept of differentials and the important property we've observed, we can treat the derivative, dy over dx, as a quotient, where dy is the differential of y and dx is the differential of x. This is true even if x is a function of t. Of course, this requires that dx is not 0. Moreover, this is the reason that, in the excellent integral notation, we can treat dx as a differential. Before we look at the geometric interpretation of differentials, we define delta y. The definition of delta y is on the screen. We can treat delta y as the function of two variables, x and delta x. By that we mean, every pair of values of x and delta x determines a unique value of delta y. Delta y is called the change in y when x changes by delta x. Note that, when x is an independent variable, we regard dx to be equal to delta x. To illustrate the definition, we work on question 7. Delta y equals f of x plus delta x minus f of x. Plug the values of x and dx into delta y. Using a calculator, we get the answer. In question 8, we calculate a differential. The differential dy is the derivative of f of x times dx. Plug the particular values of x and dx into the differential, we get the value of the differential. As we can see, the answers to question 7 and question 8 are very close. Moreover, dy is much easier to calculate than delta y because the value of the derivative of y at the particular value of x is a nice number. The sketch on the screen shows the geometric significance of dy and delta y. For a change in x by delta x, delta y represents the change in y, and dy represents the change in y along the tangent line. In general, dy is very close to delta y if dx is tiny. We'll go over another question. In the question, the differential dy is the derivative of f of x times dx. Note that the chain rule is needed to get the derivative. We'll go over another question. In the question, the differential dy is the derivative of f of x times dx. Note that the chain rule is needed to get the derivative.